And I'm going to add a little section right over here to show how you can change this into a time delay for something that would ignite a fuse. You've got this circuit here, and let's just take out those two wires, and we're going to connect those two wires to this circuit. We've already got a 9-volt battery, right? I'm not going to add a new 9-volt battery. I'm just going to draw it again. And let's put in 2 identical resistors. We'll make them both 10Ks. So anybody, what's the voltage relative to the bottom wire? We'll call this bottom wire ground. What is the voltage right here at this wire? Josh?
9.
No. So here, this voltage is 9 volts because it's across the battery. But then the current through that goes through 2 identical resistors. And I'm asking, what's the voltage? Maybe it's not clear where I'm asking. I'm asking, what's the voltage across that bottom resistor?
Is it 4.5 volts?
4.5 volts, because we've got just a standard voltage divider here. So it's going to be 4.5 volts. And let's put that into a op amp. And I've got this op amp actually wired without negative feedback. So I've got it wired as if it's a comparator. We'll talk about that in a future lab. And this op amp, I'm going to power between 9 volts and ground. All right. So now my question is, given this, we've got 4.5 volts over here, and up here, we've got the voltage source that's on our right. I'll re-graph it fast just so you can see what it looks like. So we've got this, which is going into our non-inverting terminal. And then we've got this, which is going into our inverting terminal. Let me redraw that a little bit more clearly. Yeah, so this is 4.5, and then eventually up here, we're going to get to 9. And so my question is, what is the output of this comparator going to look like? So this op amp. So what does an op amp do? It takes the non-inverting, subtracts from it the inverting, and it essentially multiplies it by infinity. So Liam, so in this region right here, up until this time, our green is greater than our green is less than our orange. Our orange is greater than our green. Our inverting terminal is above our non-inverting terminal in this first time period, this first time section, where we've got our non-inverting voltage in green less than our inverting voltage in orange. What is our output of our op amp? Remember, our output of our op amp tries to be some sort of gain, which is pretty close to infinity, times V plus minus V minus.
So is it just the difference, and then eventually the output turns?
So it's going to be the difference. Is that, what is that difference?
Trying to take it to negative infinity.
At the
Is it going to be positive infinity or negative infinity?
Would it just be 4.5 as it approaches 9 volts?
No. So let's plug this in. So for this first time span, I'm drawing in red. That's the same thing as this red standpoint. What is V plus here, which is in green, is less than orange.
So
it'll be negative. And we have to finish up because we've just finished up the class, but this will be negative infinity. But it can't go down to negative infinity because what are we powering it from? 9 volts and ground. So it can only go to really 0. In the next time period, in pink, what's the output going to be? It's still going to be always infinity times V plus V inverting, V non-inverting minus V inverting. But now what will it be? It's going to be infinity times positive infinity. And so if we draw the output of this thing, we're going to see that V versus time starts off at, from here, 0. And then it can't get actually up to infinity. The highest it can get to is what it's powered from, which is 9 volts. So
It's a step.
and then it'll just pop up to 9.
So technically, like we look at the like infinity, negative infinity, but in reality, it's only the limits of like what the power source powering it is.
Exactly. But I am going to correct my coloring to make it match the rest of what I've got. So I've got the first part is in red and the second part is in pink. And it crosses over this time right here, where it crosses corresponds to this time right here, where the sign of the inverting minus the non-inverting changes from negative to positive. This is our output, and our time here is when our output of our capacitor is 4.5. So we can solve our circuit for 4.5 is equal to 9 minus 9 e to the minus t. Solving it for t corresponds to that point. Solving it using algebra, we could subtract 9 from both sides and then multiply by -1, and we'd have 4.5 equals 9 e to the minus t. And then we could divide both sides by 9, and we'd have 1/2 is equal to the e to the minus t. And then we could take the natural logarithm of both sides, and we'd have ln of 1/2 is equal to the natural logarithm of e to the minus t, which just simplifies down to minus t. And then we could find out what our time is. It'd be equal to minus ln of 1/2. And so that's 0.693 seconds. So that gives us 0.693 seconds, about 0.7 seconds before this thing goes from low to high. So now there's one last part of this entire circuit that we need in order to build something. And that one last part is an output. So let me draw the whole thing now. We have our circuit. Here's our capacitor circuit. Time equals 0, it goes up. We've got our 100K over here, and we've got our 10 microfarads over here. And then from this, we put this into the non-inverting side of an op-amp. And I'm going to draw our, since I know I've got our 9-volt source over here, I'm going to draw it in engineering shorthand like this.
Isn't that the same way you would kind of do it on Spice if you're trying to make it?
Yeah, exactly. And then I'd power this from between ground, and I'd also power this from another 9-volt source. All right. And it's all 9-volt sources, so there's only just one 9-volt battery. It makes it easy. Now then we want to do something with this. So here's one example of something we could do. And I'll show you the circuit in a second. So this is an LED, and after about 0.7 seconds, when I flip this, the LED will go on. But if instead of just having an LED, I wanted to have something that had a little bit more power to it, maybe I want to be able to detonate a stick of dynamite. And so I bury the dynamite in a rock. I bury the dynamite in it. I want to create a road. I could then connect this to, I cannot directly connect it to a squib. This is an igniter squib. It's like a piece of nichrome wire that gets hot. And that won't work because the output of the op-amp just won't provide enough current to ignite my squib. So I just need something to increase that current a little bit. And something that will do that is this circuit. This is could be a 2N7000 FET. You'll learn how those work in electronics. Even that, there's our squib. And unfortunately, even that won't work because the squib might require 10 amps of current. And this thing out here might only be able to provide 10 milliamps of current. And this thing out here might only be able to apply 1 amp of current. So it's still not going to fire the squib. So we still need something even higher power out of this. And that higher power thing is going to be could be a relay. So we've got a relay that I'm going to draw next. And a relay is just an electromagnet. When 1 amp goes through this FET, it pulls this movable contact to the left. This movable contact is magnetic. It gets pulled to the left and it completes this circuit. And then we can have some sort of really beefy, big 12-volt car battery connected to the squib.
Is that so?
And then
what-
that will work. And now you can easily have, 10 amps or more.
Okay. So what creates the relay? Is it the relay connected to the 2N7000, or is it the inductor that creates it connected to the voltage source?
Oh, yeah. It does look like an inductor, isn't it? This is actually, this whole thing right here is one component. And it's and this thing that looks like an inductor. It's actually an electromagnet. It would function like an inductor since it's a big coil of wire, but here we're using it as an electromagnet that's going to draw this arm to the left. And it's just like a big, thick, heavy-duty switch. And so now that switch could supply 10 amps, or you could buy a relay that would support 100 amps if you want. And this is still not a great idea, because when you close your switch, you've only got 0.7 seconds to get out of there. So let's change this around. Let's now change this to 1 mega ohm. Let's change this to 100 microfarads. And now we've just increased the tau by a factor of 100. And so now instead of it being 0.7 seconds, now we've got 70 seconds after we flip that switch to get out of there. You could now bury your dynamite, put the squib in there, activate the switch, and you've got just over a minute to get out before it blows. So this is the device. You can see the 9-volt battery source. We've got a switch. And as soon as we turn the switch on, this LED lights to say that there is power supplied to our circuit. It charges up this capacitor through this resistor. And here's our voltage divider over here. This is our op amp. And when the op amp notices that the voltage on this capacitor is above 4.5 volts, it turns its output high, which then turns on this MOSFET over here, which then supplies current to the coil of this relay, and then that will turn on this light. So here it's on. Right now, current's flowing into this capacitor, charging it up, and now the light's on after a couple of seconds of delay. So we can plug something into the switch that's closed by the relay. So I'm going to attach this to this. After first turning my circuit off. So this circuit has a separate set of batteries. When it's completed by the relay, current flows through the batteries, through the switch, and then activates this squib. And inside the squib is a small piece of nitrocellulose paper. And you'll see it fire. So we turn it on, and in 3, 2, 1, LED goes on. Whoop! Dear Lord.